rocking and rolling. All right. So, chapter 6 deals with so-called Boltzmann statistics. And this is technically our first actual foray into the field known as statistical mechanics. I mean, we did do some brief stuff when we started talking about like counting the multiplicity of certain macro states, and when we talked about entropy and all of that. This is going to be more our first formal introduction to all of this. So the first section is going to be introducing the so-called Boltzmann factor, which we'll find to be incredibly useful. Oop, we don't need that. So basically what this Boltzmann factor will be, we'll just say what it is before we actually define it. It'll be a formula for the probability of finding a system in a microstate when it is in thermal equilibrium with a reservoir. And so again, reservoir is just the thing that we have defined a few times, which is just something that's so big that it can give and take energy or other quantities without actually changing itself. And so this will be in contact with a reservoir, and the reservoir will be at a specific temperature. Okay, so I'm just saying that right at the get-go, just because it's important to keep in mind exactly what this thing is and what it's going to do for us. Okay, so let's first of all just consider a single atom with some energy levels. For example, we could consider like hydrogen. That's going to be typically the most easy one to detail. So hydrogen, it's got what, a single electron, which can be moved to different energy states. If we neglect any kind of degeneracy splitting, then it has like an energy diagram that looks like this. So down here, you've got the ground state for hydrogen, which is minus 13.6 electron volts. So this is what we call n equals 0. This is the first excited state, minus 3.4 eV. And then the second excited state is minus 1.5 EV. So this corresponds to n equals 1, n equals 2. Does everybody remember how to, I imagine most people have probably taken quantum mechanics, so just a quick reminder that the state of hydrogen quantum mechanically is determined by the quantum numbers n, L, angular momentum, and the magnetic quantum number, m. Not terribly important for the moment, but just to recall. So the ground state, there's always a single ground state. There's never multiple ground states unless you're talking about something real fancy, which we aren't here. For the n equals 1, there end up being, what, 4 different states, which are all degenerate. Of course, there's a such thing as degeneracy splitting, but we're not going to mention that here. And then for this guy, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And so we're going to refer to this number right here as the degeneracy. So the degeneracy for the ground state's 1, degeneracy for the first excited state's 4, and degeneracy for the second excited state is 9. And you can show that, at least for the hydrogen atom, these degeneracy, they look like n squared plus 1. Wait. I have my labeling wrong here. 1, 2, 3. Okay. So basically, if we had some fixed atom, if we just had hydrogen sitting on its own and it was completely isolated, then whatever energy level we put it in is always going to be fixed. It's not going to change one way or the other because the system is completely isolated. But if we're going to look at non-isolated systems where something is in contact with a reservoir, then all of this changes, okay? So we'll come back to actually using those energy levels eventually, but just for now, we're just laying that out. Okay, so we are interested in so-called non-isolated systems, ones that are in contact with a reservoir. And so we're going to let energy flow between whatever the system is and whatever the reservoir is. Okay, so now let's actually start laying down some of the mathematical underpinnings of Boltzmann statistics. So let's just consider that we've got an atom, like we just said before. Let's suppose it's hydrogen or something, whatever. But let's consider two different microstates. We'll call the first one S1. Think of this as like the ground state of hydrogen. And we'll think of the other one as just being like the first excited state. Okay. So if we have these two different microstates, we'll refer to E of S1 and S2 as just the energy. So E is just going to be the energy of a specific microstate. So when it's in the ground state, this just spits out minus 13.6 eV. So E of S1 and E of S2 are defined as the energies. And we're also going to define P of S1 and P of S2 as the respective probabilities of these two different microstates. So these are the probabilities. So let's recall that if we have an isolated system, right, then all the microstates are equally probable. But here, what we're going to do is we're going to specifically consider the case where we have the so-called non-isolated system. So the system plus the reservoir, they're still isolated, but we only want to actually like formulate everything in terms of the system itself. So the system itself is non-isolated. But overall, the system plus reservoir is still an isolated system. So we can still use all of the same formulas that we had developed before for the full system itself, for the full system plus reservoir. So let's define the multiplicity for the system, or define the multiplicity for the reservoir when the system is in a specific state here. So we'll refer to those as omega sub r to denote reservoir. So this is the multiplicity of the reservoir, the number of states that exist, for the case when system is in the ground state, for example. Okay, that's what that'll refer to. And likewise, we'll define the multiplicity of the reservoir for the second excited state, so for S2, we'll denote it like that. Okay, so now let's suppose that the energy of S1 is less than the energy of S2, which it is for the case of hydrogen. So what can we say about these two multiplicities right here? Well, we can say that the multiplicity for S1 should be greater than, greater than the multiplicity for system 2. Since there's, if the S1 energy state is less energy than this one, then in this state, there's more energy left for the reservoir. So it's an isolated system, so the total energy is fixed. So if there's more energy going into S2, then that means that there's less energy left over for the reservoir. So therefore, if there's more energy in the reservoir for S1, then its multiplicity is going to be bigger than it is for S2. Okay? So, for example, we could take like omega r of S1 is probably like, I don't know, 100 or something. Omega r of S2 is equal to 50. Generally, the numbers are much, much bigger than that, but that's just a typical number for something we could be talking about right now. So now let's recall how we actually wrote down the probability for a specific microstate. So can anybody help jog our memory on how to do that? So if we want to write down the probability of being in S1, for example, for the full reservoir plus system, how would we do that? what's that going to be equal to? So there's going to be a numerator and there's going to be a denominator. Does anybody have any thoughts about how we might write that down? So I'll get you started. So it'll be whatever the total multiplicity is of the whole system, the whole reservoir plus system, is for the state S1, all over the grand total for all different microstates, right? So I'll give that a capital T, and it doesn't have a functional dependence. Let's see, omega 1 over omega 1 plus omega 2. Not exactly. So there's definitely no adding going on here. Remember that, where can I write this? So if we had two systems, right, then if we wanted to find the total multiplicity for the two systems, we always took the multiplicity for A times multiplicity for B. So that's what the total multiplicity was defined as. Because basically for each multiplicity in here, for each microstate in there, you have every single option available for system B. And so you multiply them to get the total. So that's that bit that we need to remember. So generally, this is how we're going to have to write the probability, right? It's just going to be the total probability or the total multiplicity for being an S1 all over the grand sum of all of the different microstate multiplicities. Okay, so how can we write these two pieces right here? Well, on top, we're splitting everything up into system and reservoir. So we can write this as big omega of S1, so the system multiplicity, times the reservoir multiplicity. Okay, so you're just splitting up the system into its constituent parts. And then we'll do the same thing down here. So we'll call this R tot times omega. This is kind of confusing. I should just put like R plus S to denote that this is the reservoir plus the system. Okay, so this is the total multiplicity for the system. This is the total multiplicity for the reservoir. Is everybody on board so far? This might have been explained kind of confusingly. I'll assume everybody's on board. Okay, well, if we're, yeah, Jacob. Yeah. Yeah, so we're saying that we remember that if we have an isolated system, we can write the probabilities like this, right? The probability is just going to be the number of microstates corresponding to some certain state over the total number of microstates, right? And so the system plus reservoir is an isolated system. But then let's take it and let's break it up into the system and the reservoir itself. Does that help at all? Okay, cool. Okay, so here, this multiplicity right here of S1 is just going to be 1 because we're simply specifying a single microstate. We're not talking about a macro state. We're just talking about the number of ways that it can exist in this specific microstate. So for both of these cases, this is just going to be 1, in which case this formula just becomes the following. Sorry, I'm sloppy with my capitals and lowercase. And we could do the same thing for S2, and we would get the same kind of result. So since we're also just specifying the microstate, this is just going to be 1 again. So we have the following. And now something we could do is we could take the ratio of these two probabilities. So let's do that. Let's take the ratio of S2 to S1. Okay, so in that case, we would have what? We would have this over omega R total times omega total be times omega R total times omega total all over omega R of S1. So that was basically just a real fancy way of canceling out those two factors right there to show that the ratio of the probabilities is equal to the ratio of the reservoir multiplicities for S2 and S1. So since we were specifically considering just a single microstate, we were able to set that to 1 in both points, and so it only depends on the reservoir itself. All right, so now we're going to use our definition for entropy to rewrite the multiplicity. So remember what we had for entropy. We had what? We had that S is defined as the Boltzmann constant times the logarithm of the multiplicity, omega, right? So equivalently, we could write this as omega equals e to the S over k. Okay, so I'm just going to take that expression, put it into here. So in that case, now we have the ratio of these two probabilities is just going to be e to the SR of S2. Sorry, that's hard to read. S2 minus SR of S1 all over K. And so what I'm calling SR of S2 and SR of S1 here is just the corresponding entropy that's associated with those specific multiplicities. Okay, so we took the fact that we're just looking at single microstates. Now we're looking at the ratio of the probabilities between those two different microstates. Okay, so now let's make the assumption, which is implicit to our whole formulation here, which is that the reservoir is going to be huge, absolutely huge compared to the system. So if the reservoir is huge compared to the system, then one should expect the difference between the entropy for state S2 and state S1 between this single atom being in one energy state versus another energy state, that it shouldn't really change at all, effectively. That the total system, the total reservoir entropy shouldn't change a whole lot based on whether it's in one state or the other. So we're going to treat this piece right here as being infinitesimally small. And do we have a relationship for the change in entropy when we're talking about infinitesimals? Well, yes, we do. We have the thermodynamic identity, which we can write as 1 over T times dUr plus P dVr minus mu dnr. Okay, so since we have that the system and the reservoir constitute an isolated system, we're going to have the following relationships. And so let's write them all out. So the total change in energy has to be 0, right? So therefore, the sum of the changes has to be equal to 0. We also have that the total volume, change in volume, has to be 0, the system plus the reservoir. And that's the same kind of expression again, and then the same expression again for dN total, just that none of these things are either created or destroyed. Okay? And so all of these things imply that we can always just replace the reservoir's change with minus whatever the system's change is, right? So if we could have dUr equals minus du, we'd have dVr equals minus dV, and we could have dNr equals minus dN. Okay, so one other thing that we're gonna assume here, or two other things actually, is that at least for the case right now, we're not going to consider exchange of particles. So this term will be completely neglected, and we'll throw that back in eventually if we need it. And also one thing to know is that compared to dUr, this dV is always going to be very, very, very small for almost all relevant kinds of calculations and conditions we're going to consider. So this term will be subleading compared to this one. So we can approximately just take this term right here. So we'll neglect that as well. And if we need to make amends, we'll come back and do them eventually. But this is a very, very, very good approximation. Okay, so approximately, and we'll just put an equality here because it's basically true. We'll have the following. And so I've just replaced what was dur with minus du over the system itself. Okay, and so now we can use this to rewrite our expression we had before, which was the entropy of the reservoir for state 2 minus the entropy of the reservoir for state 1. So we said that should be infinitesimally small. We have a relationship for this to the change in the system energy. So we'll put that in. And this is just also expressed as the following, where these two things are also very closely spaced. Okay, so now we can take this result right here, and we can throw it back into our ratio for the two probabilities. S2 minus E of S1 all over K times T. And rewriting that just a little bit further, just breaking it up into 2 exponentials rather than 1, we can write this as minus E of S2 all over KT divided by E to the minus E of S1 all over K times T. Okay, so we're going to call these two things Boltzmann factors right here. So this exponential is a Boltzmann factor and this exponential is a Boltzmann factor. But let's show one more thing real quick. So this is a trick that's commonly used in physics, and you've probably seen before, but possibly even waves right now, if anybody is in that, which I know some people are. It's where you take all of the functional dependence and you separate it onto one side or the other. So for example, we've got functional dependence on S2 and S1 on both sides, so we can move the functional dependence for S2 all onto one side and the functional dependence for S1 all onto the other side. So let's do that. For E to the minus E S2 KT, that's going to be equal to S1 all over E to the minus E of S1 all over KT. All right, so now what you can observe is that this side, it says that it completely depends on S2, but this side says it completely depends on S1, right? So you've got a function of S2 is equal to a function not of S2, of S1, and a function of S1 is equal to another function not of S2, or not of S1, but of S2. So what this tells you is that actually both of these sides are equal to a constant, right? Because it says this function of S1 is not equal to a function of S1. It's equal to a function of S2. So we have a special name for this constant right here. This constant is called well, it introduces the so-called partition function. And so it's actually 1 over the partition function, but this is Z right here. It's called the partition function. And if you continue on in physics, you'll see this thing pop up all over the place. In statistical mechanics, quantum field theory, which are all really types of statistical mechanics. So this is a really, really important concept, which you'll see pop up again and again. So using the fact that we have this constant that both of these things can be related to, we can write, in general, the probability for a specific state is just being 1 over whatever this partition function is, times this Boltzmann factor, E of S1, or not S1, we'll just do S right here, all over KT. So all I'm doing is I'm just rewriting this expression right here. So you could do it for P of S1. You could say P of S1 is equal to 1 over Z times E to the minus E of S1 over KT all on this side. So if we generalize that expression, we would get something that looks like this, right? So this is how we can write the probability of a specific state if we're able to find what the partition function is and we know the energy states and we have a specified temperature. So this defines the so-called Boltzmann distribution, probability distribution specifically. And so qualitatively, if we were to plot this, it just looks something like the following. So if we have E as a function of the state on this axis, we have P as a function of the state on this axis, obviously it's just a decaying exponential. So it just looks something like that. And obviously, since this is a probability, if you were to integrate from 0 to whatever the highest energy is, if that's infinity, you integrate from 0 to infinity, the area underneath this graph, it better equal 1, right? So integrate that. I don't know how to write that. Just integrate that. It should be 1, obviously, because probability is conserved. Okay, so does anybody have any thoughts about how we might calculate the partition function using the thing that I actually just said about probability summing to 1? Our energy is supposed to be discrete, though. So Jerry, energies can be discrete or not discrete. I mean, really, in like quantum mechanics, they are discrete. But we're not really too concerned about the intricate details of what specific system we're talking about just yet. We're just developing the general framework. But you'll see that hashed out a little bit more soon, hopefully. Yeah, so Jacob said summation of all the states. Basically, can we integrate to get the partition function? Yes. We can integrate to get the partition function. So here we're just gonna, rather than specifically saying that we have continuous states, we're gonna say that, well, we don't know whether they're actually continuous or not. So we'll just put a summation sign. Doesn't really matter. You could put an integration here if you want to as well. So just sum up all the probabilities. As I just said, that has to be 1, right? And so we just found an expression for the probability, so we can insert that. It is 1 over z, e to the minus e of s, all over k times t. And since z is just a constant, it can be pulled outside. So we have 1 over z, sum over s, e to the minus e of s, all over k times t. And so since this whole thing has to be equal to 1, right, we can just multiply by z, and we've got our definition of z, partition function. Well, we know how to calculate it now. So z would just be equal to sum over s, e to the minus e of s, all over k times t. And this is the point where, yeah, I mean, if these were continuously distributed energies, you would integrate this rather than sum it. But we're just going to write it like this for now. And so this defines the so-called canonical partition function. Does anybody have any thoughts about why it's called specifically the canonical partition function? So it gets the name, the kind of obtuse name of canonical partition function, because whenever we're talking about like the canonical ensemble, which we haven't really used those words, but basically the canonical ensemble is the one where the energy is allowed to vary. And so specifically here, we developed this framework only assuming that the reservoir in the system can exchange energy and not like number of particles or volume. We just neglected those for the most part. So that's why it's called the so-called canonical partition function. So you can define other partition functions that correspond to different types of assumptions, different situations. So right here, we're just going to talk about the canonical one. Okay, so let's do a little example of how we can actually use this if you were back in the early 1900s to write a PhD dissertation. I'll mean more in just a second. So let's consider the surface of the sun. Does anybody know how hot the surface of the sun is? Anybody at all? 5K Kelvin? Yeah, right around there. 5,800 Kelvin is what people typically take. Yeah, specifically here I'm saying the surface. There's a bunch of funky stuff going on with the corona of the sun actually being substantially hotter than the surface. And that's supposedly some really interesting plasma physics, which I don't understand, but maybe you could find somebody who does. So this is specifically the surface of the sun. Okay, so at the surface of the sun, let's use the fact that we know how to calculate these kinds of probabilities for hydrogen. So let's take what we had just derived before. So we were able to write down the ratio between the first excited state and the ground state. That was just e to the minus e2 all over kt, e to the minus e1 over kt. So we could rewrite this as e to the e2 minus e1 all over k times t. So we know what the ground state is. It's minus 13.6, and we know what E2 is. It's minus 3.4. So we can get what delta E is, and delta E here is just equal to, and I'll say 2.1, equal to 10.2 electron volts. And if we were to plug in roughly 5,800 Kelvin into this little piece right here, the Boltzmann constant times that in electron volts is roughly 0.5 eV. And so if you plug those numbers into here, you get something that looks like e to the minus 20.4, which is approximately 1.4 times 10 to the minus 9. So what does this tell us? Well, it tells us that if we have a billion atoms in the ground state, a billion hydrogen atoms in the ground state, that for every billion, there will be, on average, 1.4 atoms in the excited state, right? So it's incredibly rare, even on the surface of the sun, to actually find hydrogen atoms in the first excited state of the hydrogen atom. So that's wild. And if you were back in like 1920 or so, and you were just starting to look at the sun, you would see these things called Balmer lines. And they're very prominent. Does anybody know what Balmer lines correspond to? What kind of transitions? X-ray, not X-ray. So Balmer lines are just the specific transition, either emission from the first excited state of hydrogen or absorption to the first excited state of hydrogen. So they're things that either start or end at the first excited state of hydrogen. That's the so-called Balmer series. So specifically, can't talk today. What happens here is you've got the sun, it emits light. This will be a really crude model. Think of this as light spewing out of the sun. And there's some kind of atmosphere like at the surface here. So there's some kind of like cloudy mixture that's going on right there. So as the light comes out of the sun, passes through the atmosphere, if it encounters basically an excited hydrogen atom in the first excited state, it can absorb a certain amount of energy, which corresponds to these so-called Balmer lines right here. Okay? So what's wild is that although this first excited state is incredibly rare, as we just showed right here, if you look at the spectrum of the sun, you see these Balmer lines very prominently. And so back in 1925, the scientist Cecilia Payne-Gaposchkin obtained her PhD for this exact observation. So basically what she concluded was that although this is an incredibly rare state, since it's so strong, since this line is so strong when you look at the spectrum of the sun, there's just got to be tons and tons of hydrogen on the sun. There has to be, because you see this so strongly. There's just got to be so much of it that even though this excited state is incredibly suppressed, there's just got to be tons and tons of sun. So she effectively concluded that one of the main constituents of the sun was hydrogen. And apparently that didn't fly in the face of the current understanding at the time very well, because supposedly back then even, I mean, you don't think of this, just in like the early 1920s, people thought that the Earth and the sun were of roughly the same elemental composition. Isn't that wild? So they didn't believe this and they discarded it. But eventually this was accepted because there were other observations which showed it was correct. And Cecilia was actually the very first female professor to be appointed at Harvard, and also the very first department chair. So this is a little side note at the end of, 1920s was a wild time for science, absolutely. You've got quantum mechanics developing at the same time that you've got people talking about the sun and the earth being made out of the same stuff. It's just absolutely bonkers. But yeah, that's the way it was. Eugenics too. Yeah, let's not get into anything that wild or morally bankrupt. But also something interesting, which I pulled out of a Wikipedia page about Cecilia, is that apparently when she was a student, flat sun theory, God. But apparently when she was a student, she tested a hypothesis that if she prayed for, I think it was like exams or assignments or something, if she prayed for one assignment versus another one, she wanted to see whether that affected her score on one versus the other. And it was kind of funny the way this was presented in Wikipedia, because it was like, oh, she did this, found out that it had no effect, and then eventually she became agnostic for that. So yeah, it was a wild time of learning all kinds of new things in the early 1900s. So that's that tidbit of history, a little bit of interesting stuff we can do with what we already learned. Okay, I want to cover just a little touch more so that we can actually cover all of chapter 6. So I'm going to hold you. So now we're going to start the section that is titled Average Values. Okay, so let's basically suppose that rather than finding a specific probability for a state, we want to find some kind of average of a system having that property. So how might we do that? Well, one way we can kind of figure it out is just consider a simple system. So let's take an atom, and let's just suppose that it has 3 states. Let's say it's got state 1, which is 0 electron volts, state 2, energy of 4 electron volts, and state 3, energy of 7 electron volts. Okay, so now let's just take a system which has 5 atoms that are like this. So system with 5 atoms of this nature. We'll take 2 of them to be in state 1, take 2 of them to be in state 2, and we'll take 1 of them to be in state 3. Okay, so at least for this simple case, we can answer our question pretty easily. So we can ask, for example, what is the average energy? Easy question. And we'll write averages like we did earlier in the book, so just put a bar over something denotes the average. So what we would do, one way to do it is we could take 2 times the energy of state 1, because there are 2 in there, plus 2 times the energy of state 2, because there are 2 in there, plus 1 times the energy of state 3, because there are 3 in there, and then just divide by the number of atoms there are, so 5. That would get us the correct answer, which is 3 electron volts. Alternatively, you could do the exact same math, but you could think of this as being 2/5 E of S1 plus 2/5 E of S2 plus 1/5 E of S3. You get the exact same answer, obviously, because all you're doing is just distributing the 5. But the alternative interpretation here is now that these are basically the probabilities that you assign to those different energy states right here. And so this we can generalize more easily because we've got an expression for our probabilities, and we can write energy generally. So we can take this, we can generalize to the expression for average energy. So if we have S states, you would just sum over S of them. E of S times P of S. Okay, so that's really simple and intuitive and straightforward. So not too much going on there. Okay, so if we only consider systems like we were just before, then how could we rewrite this? So specifically for the canonical partition function, the canonical ensemble case. Well, we found out that we could write the probability of some certain state S as just being 1 over whatever the partition function is, times e to the minus, and here I'm going to use beta. We'll define that in just a second. This exponential term right here, the Boltzmann factor. So it's just the 1 over the partition function times the Boltzmann factor. And so here, commonly in stat phys and in quantum field theory and all kinds of other spaces, you'll see people use beta rather than 1 over kt. I feel like there's probably some historical significance to that, but just know that we'll always basically use beta to mean 1 over kt. So we can use this expression to rewrite our average energy. And so since 1 over z is just a constant, in our expression right here, we can just pull it outside of the sum. So we would have 1 over z, sum over states, E of S, times the Boltzmann factor. Okay, so that's just how you would define the average energy in the canonical case that we're talking about right here. And so likewise, if you wanted to calculate the average value of any other quantity, you would just do the exact same thing, but with that other quantity substituted in for E. So in the book, he just writes x bar. So x is supposed to represent some quantity, which is generally be the following. Whatever x is as a function of s, e to the minus beta e of s. Okay, so this defines the so-called canonical ensemble. Don't worry too much about what those words really are, though. Let's see, was there something else I wanted to say here? Oh, just a bit of a distinction. Are there any requirements on what x has to be? Not at this point in time, no. Just think of it as any thermodynamic property of the system that you could possibly think about averaging. I'm sure you could think of things that when put in here wouldn't make sense, but yeah, what's implied here is that we're averaging any kind of quantity that we would normally think of as actually being averageable. So just all thermodynamic quantities that we've described so far could be put in there. One thing that I want to note is that we've been using e's rather than u's that we did before. And so basically the reason for that is that these averages are additive. So if you take the average of E1 plus E2, that's equal to the average of E1 plus the average of E2. And so you can just sum up the averages of all of the separate energies. And so when we were talking about U before, like the total energy of a system, what we really meant was just like n, the number of particles, times the average energy of each of those particles or whatever. Okay, so that's just the distinction here, and that's how you can relate what we're talking about now to what we've been talking about. All right, there's a little bit more I'd like to get through. I'm going to talk about how we can re-understand the paramagnet, which was a really exciting topic we talked about back in, what, chapter 3? So let's discuss that a bit. So we'll be able to rederive basically that hyperbolic tangent formula that we did via some pretty complicated stuff with using like Stirling's formula and Stirling's approximation and whatnot. We'll be able to do it in just a couple lines here, so this will be satisfying. Okay, so let's remember exactly what the paramagnet was. So the paramagnet was just a system where the total energy was given by some coefficients mu times b times n down, the number of dipoles in the system that are spin down, times the number of dipoles that are spin up. So it's basically just, again, hopefully you remember, but it's some magnetic field, then you've got some particles in that magnetic field, and they can be oriented up or down, and the up or down dipoles determine what the actual energy of the system is. So this is such that we assign an energy of minus mu b to the up state, and an energy of plus mu b to the down state. Okay, so for the case of the paramagnet, it's actually really easy to calculate what the partition function is. So let's do that. So the partition function is z. Remember that it is just equal to the sum over all the states, e to the minus beta e of s, where beta is 1 over kt. So here there are only two different energy states, so not a whole lot of work you have to do. So it's e to the plus beta mu b. And I try to distinguish betas from b's, but if they get confusing, just say something. To e to the minus beta mu b. And so does anybody remember what this is? When we talked about this before, I elaborated a little bit more. Is it some trig function? We're getting close. Yeah, Jay's got it. It's basically cosh. It's actually 2 times cosh. 2 times the hyperbolic cosine, and the argument is just beta mu b. Okay, so the partition function is easy to calculate here. It's the hyperbolic cosine. Now let's calculate the probability of an up state. So that'll just be, remember, it's just 1 over z times the Boltzmann factor for that state. So in this case, it'll just be e to the plus beta mu b all over z. And also p down. So it's going to be written the same way. Oh, hold up. So we'll use the partition function here. So we'll just rewrite this. So it'll be e to the beta mu b over 2 cosh of beta mu b. P down, just do the same kind of stuff. E to the minus beta mu b all over z. E to the minus beta mu b all over 2 cosh beta mu b. Okay, so from this expression, what's a really easy way to show that the probability sums to 1? Well, what's a really easy way is you just sum them. But basically, I'm just trying to say it's really easy to see because if you recall, as I just said before, that this combination right here is going to be 2 times cosh of that argument. Well, you just get it again. You get p up is that guy, p down is that one. And so it's just going to be 2 cosh over 2 cosh. So it's just very obviously equal to 1. Okay, so let's keep all that in mind. And let's bring it over here. So let's calculate the average energy of the system, which we had actually calculated before. So this is just going to be, as we just said, we'll just sum over all the energy states and weight them by the probabilities. And so that'll just be minus mu b times the probability of up plus mu b times the probability of down. Combining that, minus mu b times p up minus p down. Oh, yikes. That's a p. So if we put everything in, we get minus mu b times e to the beta mu b minus e to the minus beta mu b all over 2 cosh of beta mu b. And at the end of the day, this is just what we had found before. It's the hyperbolic tangent of beta mu b. So we were able to find the average energy for the system. And so before we had found u is just n times e bar. So the difference between this formula and the one that we had before is just a factor of n. But we were able to find this result basically a lot quicker via this method. And so I think that's actually probably all we really need to get through today, so I'm not killing you too much, and maybe you can get outside and check out the sun because it's still really nice outside. But does anybody have any questions about all of this? This is where it starts getting fun, in my opinion. No? Okay, well, that's all we're going to cover today. Don't worry too much about it just because you do have the exam coming up on Thursday or whenever you scheduled with me. But yeah, we'll talk more on Wednesday.